Okay, well, good afternoon, everybody, or evening if you're watching this in the evening. I apologize for today's technical problems. I've contacted WebEx and they're working on it, but I guess it wasn't ready in time for our lecture today. So giving you a little more freedom with your time, I guess. This lecture is actually going to be one of probably this one and Monday, very, very key lectures for chemistry concepts. And so the content um, is something that you may have had if you had high school chemistry, but it's something that we come back to time and again in chemistry, and that is, naming inorganic compounds, as well as talking about moles. And so, more than just the animals that make a mess of your backyard or dig holes in your lawn, these are moles relating to the quantity of reactants, products, and reactions, for instance. And so it's a new chapter. So let me play the video for you to, I guess, talk context first. And so the context is controversial, probably the most controversial topic in chemistry or in the sciences, really. Climate change. And so let me put this up.
Our world is getting warmer. Since 1975, the average global temperature on Earth has increased at a rate of 0.2 degrees Celsius per decade. This world map shows the difference in average global temperature since 1885. Notice how dramatic the warming has occurred over the past decade. In fact, temperatures over most of the Earth's surface have exceeded the average global temperature by as much as 2 to 2.5 degrees Celsius. With such a dramatic temperature increase over such a short time frame, where will that leave us over the next few decades? Will the surge of extreme weather patterns become the norm for our planet? Although few people disagree about increasing global temperature, it is still controversial whether this is warming due to natural variability or man-made activities. So, do you believe that climate change is happening? Is this due to man-made actions?
I would say no, because I have no first-hand experience. Events like Hurricane Katrina or the earthquake in Haiti are just part of our Earth's natural cycle.
Yeah, climate change is real. If you look over the data of the past 50 years, then you look at the temperatures rising in the atmosphere, I would have to say that climate change is real.
I haven't really noticed a difference in my life, so I'd have to say no. It just kind of seems like media hype.
In this chapter, we will present data and chemistry to help you make an informed decision about the accuracy of what you hear in the news.
Okay, so I don't know if you recognized in the video, but that was shot, those last interviews with students, that was shot in the Biosciences building here on campus. So that kind of sums up what most people's thoughts are related to climate change. It's either media hype or it's happening, but it's kind of natural causes or natural cycles, like sunspots, for instance, or something is causing it. Or yes, it's happening, but we are to blame. It's what we call anthropogenic causes, and so that's kind of the opinions. And I wish I was in class so I could do a poll of what you guys think. It kind of depends too these days where your political leanings are. So it turns out more Democrats tend to believe that it's anthropogenic or human caused, versus Republicans are kind of I think a lot of them actually do believe that things are getting warmer. Some of them don't even really believe that, but I think in general they do believe kind of in warming cycles in recent years or recent decades, but they really believe it's nothing that we can cause or that we caused, or there's really nothing we can do about it. And so I'm going to kind of stay neutral on it as much as possible and let the data speak for itself in this chapter. And so as you do your reading and as we talk about the context here in the lectures, you can kind of draw your own conclusion and make up your mind, is it 100% anthropogenic, or is there some, natural causes as well in there? Okay, so, kind of make up your own mind with it. All right, so these are the topics that we're going to talk about in this chapter. So today we're going to talk about the carbon cycle. So what are the reservoirs of carbon, and how does it move through those different reservoirs? We're then going to talk about greenhouse gases. And for this, we have to really get into something beyond Lewis structures, and that is the shapes of molecules. So we're going to get into that a little later. And then we're going to, these last bits here are kind of the context. So we're not really going to talk chemistry, but we're going to, really talk about what is climate change, how does it differ from global warming? It used to be called global warming. Why did they then change it to climate change? Was it just semantics, or was there a real point to that? And then, end the chapter with thinking about, how can my daily actions affect our environment? And so what can we, as citizens of this globe, what can we do to improve the environment for, future generations? Okay, so the carbon cycle, I'm going to show you this, figure here from the book. And I've got, a little short, couple minute video just to kind of, bring it to life a little bit better. But shown here in the black, so all these like forests, soils, carbonate minerals and rocks, fossil fuels, and sand, silt, in an ocean, and then you've got surface water. All of these in black are the reservoirs. So that is where carbon in different forms is stored. Okay, so surface water, deep ocean, that would be just CO2, really. Fossil fuels, that is as petroleum products, so really a lot of carbons involved in those. Carbonate minerals, those are inorganic compounds, so things with carbonates as a negative ion, and we're going to talk about what that is here shortly. And then, so all those are reservoirs, and then how carbon moves through the system is shown in red. And so you've got, evaporation of CO2 from the ocean, and then deforestation pumps CO2 into the atmosphere, as well as respiration. Photosynthesis, removes CO2, okay, and puts it into soils, for instance. And then burning fossil fuels results in a lot of CO2. So these kind of correspond to producing CO2, and then, for instance, photosynthesis using it, taking it out of the system, for instance. But, if you look at these numbers, it's pretty astonishing. This is, per year, 750 gigatons of carbon in different forms make up this carbon cycle. And so we've got, a lot, 61 gigatons per year, for instance, is taken out by photosynthesis, but then respiration is 60 gigatons, okay? And so, so really kind of astonishing of, just in the atmosphere, this is just the atmosphere, you can have 750 gigatons of carbon, really as CO2, essentially. There's a little bit of CO, but it's mainly carbon dioxide. Okay, so I think, I think in maybe chapter 2, we talked about the air we breathe, and one of the gases in the atmosphere we said was carbon dioxide, and I think we threw this number out then. So it's really a small number. This is parts per million, right? So only 400 molecules of CO2 per million of other gas molecules. Okay, so it's not much, but as the data will show, it makes a huge difference in global temperatures. Methane is another greenhouse gas, much less concentration, and carbon monoxide is even trace less than that. So that's one of the three main reservoirs for carbon, and then the other is carbonate-based rocks, fossil fuels, and soils. And then the third is plants and animals, and that's where carbon atoms are combined with oxygen, hydrogen, nitrogen to form our building blocks. So carbohydrates, proteins, and lipids. Okay, so that's kind of an overview of the carbon cycle. I just want to show you this video, which actually went away. There we go. Okay, so I'll show you this video on the carbon cycle just to kind of bring that figure to life.
Carbon is an element that's found nearly everywhere on Earth, in the atmosphere, the soil, the ocean, and deep inside the Earth. It's also the main ingredient inside of every plant and animal, including you. Carbon doesn't stay in one place or in one form. Instead, it moves around between different parts of the Earth. This process is called the carbon cycle. Let's look at the atmosphere. Here you'll find carbon in the form of a gas called carbon dioxide. There are many ways that carbon dioxide moves into and out of the atmosphere through natural processes. For example, one way carbon dioxide is taken out of the atmosphere is through photosynthesis. Plants take carbon dioxide out of the air and use this carbon to build their leaves, stems, and roots. That means plants store carbon. When animals eat plants, they use this carbon for energy and to build their own bodies. One way that carbon dioxide gets into the atmosphere is when plants burn in a wildfire, and their carbon is converted back into carbon dioxide. Carbon dioxide also goes back into the atmosphere when plants and animals die and decompose. In certain places, like swamps and the bottom of the ocean, dead plants and animals don't completely decompose, and they end up buried in layers of sediments. Over millions of years, heat and pressure turn the carbon from these plants and animals into fossil fuels, like coal, oil, and natural gas. The ocean also plays an important role in the carbon cycle. Ocean water absorbs carbon dioxide from the atmosphere, but also releases carbon dioxide back into the air. All these different parts of the carbon cycle should be in balance, but people's activities are disrupting the cycle and knocking it out of balance. When we burn coal, oil, and gas to create energy, we're taking carbon from deep underground and putting it into the atmosphere faster than natural processes can take it away. After all, it took millions of years for those fossil fuels to form. Now the atmosphere is getting overloaded with carbon dioxide. In addition, when we cut down forests, that leaves fewer plants to take carbon dioxide out of the atmosphere. Here's another way to think about it. Imagine the atmosphere is like a big bathtub, and carbon dioxide is the water. In the natural carbon cycle, the amount of carbon dioxide that goes into the atmosphere is balanced by the amount that goes out. It's like putting water into a bathtub, but letting the same amount go down the drain. The water level in the tub stays the same. And that's exactly what should happen with the amount of carbon dioxide in the atmosphere. But what happens if you add water to the bathtub faster than it can drain away? The tub will fill up and eventually overflow. Something similar is happening in the atmosphere. People are burning lots of fossil fuels and adding carbon dioxide to the atmosphere faster than it can be removed. So the atmosphere is getting overloaded with carbon dioxide. Carbon dioxide is a greenhouse gas, which means it traps heat in the atmosphere and keeps the Earth warm. So all this extra carbon dioxide is making the Earth warmer and causing the climate to change. It's a big problem, but we can solve it. One big part of the solution will be to reduce our carbon dioxide emissions by burning less coal, oil, and gas. This will help bring the carbon cycle closer to its natural balance.
Okay, so let's talk about this reservoir in a little more detail. So that is carbonate-containing rocks, or I guess just the rocks part of it, which relates to inorganic compounds. Okay, if I can go, there we go. And so I guess before that, so just the emissions. So the global CO2 emissions. I guess what industries or what is responsible for pumping a lot of CO2 into the atmosphere. Not surprisingly, it's our power stations. So especially coal-fired power plants, but even natural gas powered power stations. Industry releases a lot of CO2. Deforestation, as the video said, now there's less trees, for instance, to absorb CO2. And really, transportation, like burning fossil fuels for vehicles, that's down the line, really. And diesel for growing fields, planting, etc. If you add those together, that's, I guess, fossil fuels for agriculture or transportation. That's then more than our power stations. So I guess transportation fuels are kind of 27% responsible, or more than a quarter of our CO2 emissions come from those transportation, agriculture. Okay, so ionic compounds. So the first thing I want to go through are the preferred charges for different groups in the periodic table. And so this figure shows kind of what the different groups, what charges they prefer, and without getting into a lot of details why, remember that everything likes to adopt the same electronic configuration as the group 18s, okay, or the noble gases, right? So these groups of elements are really unreactive. They're really inert, we call them. Okay, and so very stable electronic configurations. And so if you have a group like the group 17 or the halogens, they are one away from this configuration. So for instance, fluorine is one electron short of this noble gas, okay? And so it would like to add one electron to become neon, okay? And so that's why, electrons are negatively charged, right? And so the group 17s, if they can add one electron to get to the noble gas configuration, that's why they're F minus, okay? So they all have a -1 charge, okay? And so you can have different charges for these, but the majority of the time, group 17s will have a -1 charge, okay? And then likewise, the group 16s, they are 2 away from the noble gases, so that's why you'll see here a -2, okay? So they have a charge of -2. And then the group 15s, they tend to be -3, but you can also have some group 15s that will be +5 as well, right? So just to show you, so if you have nitrogen, it could lose 1, 2, 3, 4, 5, and now you're back to helium's configuration. Okay, so if you're losing electrons, that's where the plus charge comes from. Okay, and then the minus means that you are gaining electrons. Okay, 1 electron or more. Okay, and so the group 14s, a charge isn't really listed there, and so group 14, it can either be -4 or +4. So you're kind of right in the middle. So it can gain 4 to get to this one, or, whoops, it can lose 1, 2, 3, 4 and go back to helium. Okay. When you get to boron, so that's the group 13s here, you really it would take too much energy to add electrons, so we generally will say they're just +3. Okay, so they really cannot be, I guess it would be like a -5. Okay, so these, I guess the ambiguity is kind of gone, right? So it's just +3, and that's the group 13s. And then we kind of skip this group, so we're going to talk about this later today. So the transition metals. And so then we'll look at group 2 and group 1. Okay, so group 2, hopefully everybody can see, if I have magnesium, for instance, it can lose 2 electrons to get back to neon. Okay, and so that makes it +2. So all these will be +2. And then these ones are just 1 away from the noble gases, and they can only lose 1 then. So lithium, if it loses 1, it's back to helium. Okay? So group 2 is +2, and then group 1 is +1. Okay? And so that those are the preferred charges for different groups. Okay? So really the only ambiguity is really the group 14s and group 15s. Okay? And I'm going to talk later today about how to know, like how do you know group 14, whether the carbon, for instance, is +4 or is it -4? Okay, the answer is it depends on what it's partnered with. And then with nitrogen, again, it can be either -3 or +5. Okay, but other than that, most of the time, these are the preferred charges for oxygen, sulfur, selenium, tellurium, so all the group 16s. It's going to be -2. These are always going to be -1. Okay? All right. And then there are some exceptions. So you'll see, the group 14, for instance, I said could be either +4 or -4, but down lower, like tin and lead, you have +2 as a possibility. And that's called the inert pair effect. Okay, so you'll generally see that as you go down a group, you have an electron pair, so 2 electrons, that is, are harder to remove. Okay, and it's really complicated to explain. Okay, so it's really due to relativistic effects, which sounds like a mouthful. It's really, Einstein's theory of relativity. It's related to that, where, if you have electrons that are close to the nucleus, they're bound pretty tightly, right? Because electrons negatively charged, the nucleus positively charged. But if you have electrons, like let's say way out here, okay, so pretty far from the nucleus, their speeds kind of in this orbit they're really not bound so tightly to the nucleus, and so they approach relativistic speeds, which means that they can approach the speed of light. Okay. Okay, and so because of that huge speed, what happens is that their orbit kind of goes in a little bit. Okay, so it shrinks. So now kind of the orbit goes to this. And so now it becomes a little closer to the nucleus. And so that makes these electrons now more tightly bound and harder to remove. Okay, so that's really without getting into math, that's really a hand-waving explanation. And don't worry about having to reproduce that on exams. That's way, way, way beyond the scope of this class. It's just kind of trying to show you why you can have some that don't follow the rules. Okay, so for instance, tin and lead, why can it be +2 instead of +4? Okay. All right, so those are the preferred charges, and we're going to exploit that now when we're talking about naming compounds. Okay, so let me review the names that we have talked about so far. Okay, so that is molecular compounds. Okay, so remember the name for that is you needed a prefix, then the first nonmetal, and then the prefix and the second nonmetal. Okay, like this would be, I'm going to pause here so you can say the name as you're watching this video. So I'm sure everybody knows this, so you shout it out. Diphosphorus, pentoxide. Okay? And so you need the prefixes for these. Okay? And then the other name that you looked at naming were for hydrocarbons. Okay, and in particular the ones that were this. Okay, and then you needed a certain prefix, and then an ane suffix. Okay, so for instance, this one was methane. Okay, so this suffix indicates this ratio where it's x and 2x plus 2. And the meth indicates that you have 1 carbon. Okay, so remember mother eats peanut butter, right? Meth, eth, prop, bute, and then the rest are the same, like pent for 5, hex, hept, oct, non, and dec. Okay? Okay, so those were the 2 types of compounds we already looked at naming for. The ones today, so we're going to look at inorganic. Let's look at, actually, let's talk about this. We'll just call these ionic compounds. So instead of molecular compounds, these will be ionic compounds. And the big thing to remember is do not use prefixes for these. So there will not be di whatevers, tris, tetras, none of that for these compounds. Okay? And so the name is just going to be whatever metal cation. So cation just means a positive ion. Positive charged ion. Okay, and an anion, whenever I throw that term out, that's just going to mean a negatively charged ion. Okay, so for instance, a cation would be like Na+, and an anion would be Cl-, for instance. Okay, and so looking at these names, so if I'm going to throw a really easy one at you first, okay, that is an ionic compound. And you know it's ionic because you've got a metal and a nonmetal. Okay, remember so you can compare that with molecular compounds, like the one I just put up. You've got 2 nonmetals. Okay. Okay, so as soon as you have a metal with a nonmetal or more nonmetals, that is an ionic compound. Okay, and so the naming for this is just you put whatever the positive species is, and that will always be written on the left side of the formula. Okay, and so you put that, so it's sodium, and then you put the nonmetal, which is the right side of the formula. Okay, and that's chlorine. And so you're going to use a suffix of IDE. Okay, so NaCl is just sodium chloride. It's not sodium monochloride or anything like that, or monosodium chloride. Okay, it's just sodium chloride. Okay, and the one shown here, NaF, is sodium fluoride. Okay. All right, so you're never going to use these prefixes. Okay, so let's look at some other examples. So this one, okay, calcium oxide. Okay, so again, on the left side is your positive species, on the right side is your negative species, and so this is just calcium oxide. Okay. And there's no subscripts for these because the charges balance each other out. So remember from this slide, right, that calcium likes to form a +2 charge, and oxygen likes to form a -2. Okay, so both of those balance each other out. So the overall charge has to equal 0 if this is neutral. Okay, as long as you don't have a charge for this overall compound, then everything has to equal 0. And so if you have +2 here, then that has to be just a -2. Okay, so the flip side of that would be sodium oxide. Okay, so this, we want to go from its name to what its formula is. Okay, and so the way to do this is just write what their preferred ions are. And so sodium likes to be that. Oxide, we saw above, likes to be this. Okay, and so the question I have for you is, how do you balance these out so that you end up with a 0 charge overall? Okay, so in other words, if you just put these together like that, you're going to end up with a net -1 charge, right? Because this is a +1, but that's -2. So that's going to be a -1 charge. Okay, so how can you put these together, a sodium and oxygen, so that everything will balance? Okay, and so if you think about that for just a few seconds, I think some of you are seeing what needs to be done. Okay, it's not like balancing an equation, so you really can't put a 2 here or anything like that. Okay, but what you can do is put a subscript here. So what if you do this? Okay, so now this is implying that you have 2 of something that has a +1 charge, so that's a +2. And then you've got a -2 over there for the oxygen. So now you have +2 -2, okay, and the charges cancel. Okay, so sodium oxide is Na2O, okay, and so this is where it's very, very tempting on an exam, for instance, to say that this would be disodium monoxide, Okay, it is not. So again, no prefixes. Okay, fight that urge. Okay, it is just sodium oxide. All right. All right. So what would the name for this one be? Okay, and I guarantee you on an exam, some possibilities would be maybe this one. That. Whoop. And yeah, maybe another filler one or something. But yeah, these are common ones. Okay, so calcium chlorine is wrong, right? Because the last part of it you always need for these ionics, an IDE suffix. Okay. This has prefix in it, so that's wrong. And so it is just calcium chloride. Okay. And this subscript just is there because you have to, again, balance the charge, right? So each chlorine is a -1 charge. So if you have 2 of them, that's a -2 that balances out the +2 of calcium. Okay, so now +2 equals -2, okay, or cancels -2. You end up with 0 overall. Okay? All right. So you can see some other examples where sodium sulfide, okay, the sodium is a +1 charge. Sulfide carries a 2-, and so you need 2 sodiums to balance out the charge. Okay, this is a tricky one. So aluminum oxide, okay, again, it's not dialuminum trioxide because you have a metal and a nonmetal. And this one, aluminum likes to form a +3 charge, oxygen a -2, so you need, in this case, let me write this one out. Okay, if you're looking at charges, you've got 2 of something that likes to be a +3 charge. And then you've got 3 of something that likes a -2 charge, so it's a -6. Okay, so again, +6, -6. Okay. And then barium chloride, I guess it's the same really as calcium chloride that we talked about. Okay. All right, so what would it be? I guess I can talk about some other of the suffixes too. So if you have, let's see, so the group 17s, they're kind of easy. So whatever the element is, so if it's fluorine, then it's going to be fluoride. Okay, so fluoride, chloride, bromide, iodide. Okay, so those are not so difficult. If you have oxygen, we saw that that's oxide. Okay, sulfur, sulfide. If it's selenium, then that should be selenide. And I guess, yeah, we already went through this for the nonmetals, I guess. Yeah, so I guess you've seen these. Yeah, and Te is telluride. Okay. Whoop, that's bad. Okay, telluride. Okay, so yeah, I guess we've seen these before. Okay, so I guess nothing too new for this group. Nitride, phosphide, arsenide, antimonide. Okay, and then you've got carbide, silicide for silicon. Okay. And that's pretty well it for the nonmetals. Okay? All right, so here's a question. What would the formula be for sodium phosphide? Okay, so we'll do that one first. And then let's do kind of the formula to the name. what would the name of this one be? That. Okay, so you can pause the video maybe instead of me just, so there's no dead air here. Pause the video, take a stab at it, and then replay. Okay. And so sodium phosphide, the strategy is to just write out their ions. So phosphorus, if you look back, phosphorus is in this group, so it likes to be a 3- charge. Okay, and so putting those together, that would have to be Na3P. Okay, so now you've got a +3 to go with the -3 charge. Okay, and then this one, just to verify the charges, so carbon can either be a +4 or -4. And so since it's on the right-hand side of the formula, that tells you it has to be a negative charge, okay? And calcium always likes to be a +2, okay? And so that's why you needed 2 of them to give you a +4 to match the -4 of the carbide. Okay, so this would be calcium, and then whatever is the nonmetal with an IDE suffix. Okay. All right, so those are the names for simple ionic compounds. Okay. And so now the last group of names, I think this is, I guess, the fourth category, are transition metal compounds. Okay, plus tin and lead. Okay, so those are some exceptions there. For these ones, it's not good enough to say just iron oxide, for instance. Okay, so if you say iron oxide, it really could be this, or it could be that, or it could be this. Okay, those are some common iron oxides. Okay, so which one? Okay, if you just say iron oxide. And so for transition metal compounds, what's so different with these is that they form a variety of oxidation states. Okay, and so what is the charge of iron in this one, do you think? Okay, so looking at it, oxygen you can assume is -2, and so that means that the iron would have to be +2. Okay. In this one, oxygen again is -2, so that's going to be a total of -6. So this whole other side has to be +6. But there are 2 of the irons, so each are +3. Right? So in this case, iron is 3+. Okay, and then in this one, this is a tricky one actually. So oxygen again being -2, so this whole other side is going to be -8. So this side has to be +8. But there are 3 of those. And so it's really, 8/3. And so it's kind of between 2 states. So some of the irons are 2 and some of the irons are 3. Okay, so this works out to what is it, 2.67. Okay, so it's kind of between a 2 and a 3 as far as the charges of the iron. Okay, and so I'm kind of pointing out that that's why iron oxide is not sufficient, because you don't know what charge the iron has. Okay, so when naming transition metal compounds, you have to explicitly say what the charge is in parentheses. Okay, and so for instance, this one, where you have iron 2, you have to say that this is iron 2 oxide. Okay, so Roman numerals say what the charge is, and just kind of for formatting, there's a space in here, but there's no space between the name of the metal and what its charge is. Okay, and so that would be iron 2 oxide. This one, since it's iron 3 in it, okay, that would be iron 3 oxide. Okay, and so be very careful, because again, on an exam, I guarantee you one of the answers will be iron 2 oxide for this one. And I know it's really tempting because you see the 2, so you want to go for that one. But remember, this subscript has nothing to do with how many there are. Okay, it has to do with the charge. Okay, so this Roman numeral doesn't have to do with there are 2 of them. It has to do with that. Okay, so always remember that the Roman numeral is the charge of the metal. Okay, and so ones that get confused a whole lot are these ones. Okay, for that reason. Okay, so this one, if oxygen is -2, then that's copper 2. Okay, and so for this one, since oxygen is -2, each of the coppers are +1, right? So you have 2 times +1 equals +2. Okay, that matches the -2. And so the name for this one would be copper 2 oxide, whereas the name of this one is copper 1 oxide. Okay, even though this has a 2 and that has a 1. Okay, so yeah, kind of look at this example and really kind of work out that since the charge of the metal is +2, that's why you need a 2 for the Roman numeral. And since the charge on copper is +1, that's why there was 1. Okay? All right. This one is a little more complicated. So manganese 6 oxide. Okay, so we're going to start to talk about some compounds where it is not neutral overall. So in other words, all of these charges don't add up to 0 necessarily. And so for this one, MnO4 and then 2 minus. Now everything has to add up to -2 instead of 0. Okay, so note the difference. Okay, this one, if it's not given any charge, you assume that it's 0. Okay, this one, you're told explicitly it's -2. Okay, so for this one, everything has to equal 0, but for this one, everything has to equal -2 for charges. And so looking at this one, where everything's neutral, you have -2, and then you have 2 of them, so that's going to be -4. So that means the manganese has to be +4. Okay, because everything has to equal 0. For this one, you now have -8, right? So 4 times -2. Okay, and so now in this case, instead of it equaling 0, you have to equal -2 because that's the charge. And so this one, it would be manganese 6 plus. Okay, so 6 minus 8 gives you the minus 2. Okay, so that's why this one would be manganese 6 oxide. Okay. All right, so just when you thought life couldn't be any more complicated, there's this slide, okay? And so far we've looked at, very simple anions, or the negatively charged part of compounds. So for instance, this one, let's do aluminum phosphide. Okay, and so there it's aluminum 3 plus. Phosphide is just a phosphorus with 3 minus, and so it's just ALP. Okay, so that's the ratio there, or the formula. And so we've dealt only with these where you just have a single element. Okay, but in practice, and what we were talking about on the carbon cycle, is you've got these carbonate-based minerals a lot of the time, or phosphates, sulfates, a lot of other ones too. And so these are more complicated anions. And so just to put your minds at ease, on an exam, I will provide this table for you, so you don't have to memorize the names or the charges of these, okay? But you have to know how to use them. And so, for instance, some typical questions would be, what is the formula for, let's do this one, calcium hydroxide. Okay, so now it's not as simple as just an O2 minus or something like that, but you have to remember hydroxide is, and you can read it off the table since I'll give it to you, okay, is OH minus. And then remember that calcium is 2 plus. Okay, so the way you would put these together is Ca, and now you need 2 of these, don't you? Because again, this is assumed to be just a neutral compound. Okay, so unless you're explicitly told that it has a charge, assume that it's neutral. Okay, and so that means then that you have that, and you need 2 of them. So now as far as charges, you've got 2 of something that is a minus 1, so that's a minus 2 to balance out the plus 2. Okay? What would I always think that it's harder to go from the name to the formula, really, because there's no prefixes or anything here. So if I, for instance, were to give you this one, okay, you're already told what kind of the ratio is between them, and so it's just a matter of kind of looking for this in the table and seeing that this is the nitrate anion. Okay, and so this would be just sodium nitrate. Okay. So let's see, what's another good example? How about, what is the name for, or the formula for iron 3 sulfate? Okay, so pause the video and take a stab at that if you can. Okay, so iron 3 sulfate. So again, the name itself tells you what the charge is. Okay, and then sulfate, you can read off the table here, and that is right here. Okay, sulfate is SO4, and then a 2 minus charge. Okay, so to balance out these charges, you're going to need 2 of these, and you're going to need 3 of those, right, to end up with a -6 and a +6 overall. Okay, so that means then Fe2, and then what you do for these complex ones is you have to put those in parentheses. Okay, and that indicates that all of this, okay, that's 1 unit, that's the sulfate unit, and you have 3 of them. Okay, so as I showed up here with nitrate, if there's just 1 of them, you don't need parentheses around it. Okay, it's only if, you know, it's 2 or 3 or whatever. Okay. All right, what about this one? So let me just put what about that? So calcium phosphate. Okay, so calcium, 2+, phosphate from the table is that. Okay, and so now it's going to be Ca3PO4, all that times 2. Okay, so now you've got each of these are -3 times 2 gives you -6. And each of the calciums are +2 times 3 equals +6. Okay, so they cancel. All right, so again, for exams, I will give you all of these. You'll notice all of them are negatively charged, except the only one that is positive is ammonium. Okay, and an example of that, let's say, I'll give you ammonium. What about this? Ammonium sulfide. Okay. And so do not make the mistake. I have students in my other class who are making this mistake. When they see sulfide, they think it's this. Whoops, 2 minus. No, this is sulfate. Sulfide is just this. Okay, so if it's an IDE suffix, that just means it's element itself. Okay, so don't try any of these. So notice the prefixes in all of these are either ATE, well, I guess there is one, yeah, I guess the hydroxide, but all the rest are like ITEs, ATEs, those kinds of things. Okay, so yeah, so this would be S2 minus, and then this is NH4 plus. Okay, so this one, ammonium sulfide, you're going to need 2 of these to balance out the sulfur. Okay, so now you've got -2, and this one you've got a +1 times 2 is +2. Okay, so +2 goes with a -2. All right. Okay, so that is naming ionic compounds. And again, both of these types, whether it's just, you know, the group 1 and 2s or transition metals, you will always have a metal and a non-metal part to it. Okay, so that's where you, you know, don't use your prefixes. Okay, so I don't know if you can hear my cat meowing in the background. She wants in the room badly here. Okay, so that is naming compounds. And again, you know, where we kind of use that is just really with the carbon cycle at this point. But when we get into talking about water later, you're going to look at even more examples of these salts. And we'll go beyond it to say, okay, which ones are actually soluble in water and which ones aren't, and we'll take it a little step farther. Okay, so I know I've hit you with a lot in this one lecture, so I just want to talk about this really briefly. We already talked about this really, so this is just a review of where do these atomic masses in the periodic table come from. And so as you recall, we talked about the different isotopes that are prevalent. And so carbon has 3 different isotopes. So this would be carbon-12, carbon-13, carbon-14. And based on their natural abundance, you just do a weighted average, okay? And so that's where in the periodic table you'll see carbon has a mass of 12.011, okay? And at this point previously we talked about the unit for that as being this unified mass unit, or just U, okay? And so here I'm going to talk about a different unit for that. So, if you look in the periodic table, you'll see 12.011 U. We can also say that it's 12.011 grams per 1 mole, okay? And so 1 mole is a very, very large number of something, okay? And so if you have 1 mole of anything, and I mean anything, like something that's insanely hard to find right now with coronavirus, are eggs, for instance. If you have 1 mole of eggs, that means you have an Avogadro's number of eggs. Okay, so this is called Avogadro's number. Okay, and it really says how many particles per 1 mole. Okay, and that's really the shorthand term for mole. We just drop the E. Okay, so we've got that many particles for 1 mole, and it doesn't matter what it is. Okay, and so all of the numbers in the periodic table for atomic masses, those are going to be how many grams if you have 1 mole of that substance. Okay. And so the mass number, for instance, okay, or the the overall weighted average of all the isotopes, okay, that corresponds to how many grams you have for 1 mole. Okay, so the SI definition, or the standard definition for a mole, is if you have a number that's equal to the number of carbon atoms in exactly 12 grams of pure carbon-12 isotope. Okay, so it sounds like a whole lot, okay, but really it's just saying that you have exactly 12 grams. So this number, it's not exactly 12 because it's considering C13 and C14 in there, okay, but if you have exactly this isotope, then it should be exactly 12 grams, okay, for 1 mole. All right? And so 1 mole of carbon has that many grams, okay? And so if you have 36 grams of carbon, how many moles would you have? Okay. And so you can, set up a little ratio, if you will, okay, where you've got 36 grams, and if you have 1 mole equals 12 grams, so that grams of carbon cancel, then that would give you 3 moles. Okay. Another way that you can think of moles, grams, and whatever is to set up this little flow chart. And so you can refer back to this throughout the semester, and it may help you, where you've got moles in the middle, number of something, and then grams out here. Okay, and then to get out of moles, you're going to multiply by something. To get back to moles, you're going to divide by that same parameter. Okay, and so between moles and number of something, that's where we're going to use Avogadro's number. Okay, so that's 6.02 times 10 to the 23rd. I will provide that to you on exams as well, so you don't have to memorize it. Okay, and so you're going to multiply or divide by Avogadro's number here. And then to go between moles and grams, that's where we're going to use the molar mass. Okay, and that is so either molecular weight or molar mass. Okay, and so the molar mass is, we're going to talk about that next lecture, where you're just really adding up all of the different atoms in the compound. And so, for instance, the molar mass for, let's look at, well, the molecule of interest here for climate change, CO2, you would just add up whatever the periodic table says for the atomic mass for carbon, so that's 12.01. And if you look in the periodic table for oxygen, you'll see that. Okay, and again, these units are grams per mole. Okay, and then you just add these up. Okay, so you've got 1 carbon, so that's 12.01, plus you've got 2 oxygens. Okay, 15.9994. Okay, and so that, it's about 16 times 2, so it's, 32, 40, so it's 40, about 44. I'll do this, okay. So 44 grams per mole, okay, would be the molar mass, okay, for CO2, for instance, okay. So that's all molar mass is. All right, so for this question then, if you have 36 grams of carbon and you want to know the moles, okay, you would just really divide by, in this case it's just carbon, so there's no real molar mass, it's just atomic mass. And so in this case you really just divide by the atomic mass for carbon, which is 12.01. Okay, and that's where you get your 3. Okay, so if you want to do it like this, that is totally cool. And it's usually, it's using what we talked about, dimensional analysis. But you can also use this scheme too. If you kind of keep this flow chart in your mind, and again, if you want moles from something else, you're going to be dividing by something. But if you have moles and you want the number, for instance, then you're going to be multiplying by Avogadro's. Okay, so that is where we will pick up on Monday, is really doing a whole bunch of conversions between grams to moles, moles to number of things, and we're going to take off on this and do a variety of different calculations. So hopefully we'll be back live by then. So anyway, I hope each of you have a good, safe weekend, and I will see you hopefully live on WebEx on Monday. All right, take care.